right? But remember, I also have water. Where is the selectively permeable membrane? What is a selectively permeable membrane?
Is that something like when we talk about like the sodium pumps and everything?
They're located in it. So that tells me
like a phospholipid.
My phospholipid bilayer, which is the membrane for all of this. Because the membrane of my cell is a phospholipid bilayer. The membrane of my vessels is made up of cells, and therefore phospholipid bilayer. So now I'm in a situation where in my bloodstream I have a water component. Out here around my cells is extracellular fluid. Does everybody remember that? Which is a water component. My cell has a selectively permeable membrane, which on the inside is a water component. Is everybody following me? Okay? So, based upon osmoles, all right, if osmoles are high in the blood, meaning there's a lot of stuff in there, okay? So let's say osmoles are high, but I'm not drinking the fluid I need. So what have I done to the water component of my blood? I have decreased my water component. But at my tissues, okay, where I have a water component, let's say that my tissues water level is normal, but this isn't in my blood. Which way is water going to move? If it's normal, or let's say high in my extracellular fluid, which way is my water from my tissues is going to move into the blood? Now, my tissue fluid is going to be low, but my cells are normal, or let's say high. Where's the water going to move now? Okay, if my blood was low, extracellular was okay, it went from extracellular to the blood. Now, my cells, which are okay, but extracellular is low, which way is the water from my cells going to move? It's going to go out to my extracellular fluid, which is going to put it where? Inside the blood. And what's that going to do to my cells? Kill them. And it can work in the reverse. It can actually create a situation where the water remains behind in my extracellular fluid at my tissue level, and the blood stays low, and the proteins and the wastes that are in that extracellular fluid retain that water in that extracellular fluid, and then I end up with swelling, which will still kill my cells. This happens a lot in cases of people who have heart failure, COPD, lung problems. Their body, the fluids stay behind because other materials, such as the waste, the nitrogenous waste, or something such as the CO2 levels. They're remaining behind in the tissues, affecting the movement of water, and the water stays behind, and the person has fluid buildup. Hold on, Nate. Alex?
So in that case, would drinking more water actually reduce the swelling?
Not necessarily. Usually in the beginning of people who are going to have these chronic diseases, usually in the beginning, yes, they can try to work on that fluid removal, but as the disease progresses, they're going to become dependent on certain medications like diuretics, okay, to try to remove that fluid. And in some cases, tubes might need to be inserted, incisions might need to be made. It just depends, because as the disease progresses, the ability for the body to handle the situation decreases to a point that it can't no longer. Kidney disease, for example, basically the kidneys can't handle it. They're not functioning correctly, and yes, the fluid stays behind in the tissues. And it doesn't matter about the fluid intake of the patient. They have to go get the dialysis.
So is this kind of referring to like edema?
Edema. Mm-hmm. Yes. And there are lots of disorders that are going to bring that about. Emily?
So I'm wondering, on like a day-to-day basis, you know, most of us aren't getting the water intake that we need. So I mean,
Eventually,
people are pretty healthy. I mean,
well, now, depending on how you want to define healthy, okay?
You go to your doctor checkup, you know, and they're like, oh,
Yeah.
you're healthy, you know.
Yeah. Well, you're going to be, you know, they may not be getting the water intake they need, but they might be drinking the sodas, the tea. But those are really diuretics and everything, and they're not as good. But, got to remember, younger cells handle things better. Okay? So, the strains that in youth, and I wish somebody would have taught me this in my youth, okay? The strains that you place on these tissues and cells of your body while you're young, it will come back to you. I am walking proof of this, okay? I'm looking now, and it's like, oh, wow. So not drinking that water all my life has been bad. And my doctor about, yeah. And so basically, they're not exercising all my, yeah, you know. And so, you know, and I will tell you, I was a smoker. Okay, I have been smoke-free now for over a month. Yay me, okay. However, I know now that, wow, that little Surgeon General's warning is true. I know that I'm going to get to look forward to probably COPD, okay? And I'm just like, so, why didn't I listen? Because I know when I was younger, I thought I knew everything, okay? And trust me, I'm at an age now where I've learned I'm not, okay? No, every day I'm learning something new. So it is very true. So yes, the body will handle it to a point. I know. You're sitting there and you're like, no.
And you're like, I need to go refill my water.
I know. We're sitting here and you're thinking, no. Yeah. Okay. The other part about this, we've kind of already talked about, okay? Because I keep mentioning, blood is a colloid, which means these pieces, okay, these pieces are getting to keep their hold, okay? They're getting to stay whole. And yes, that is pressure, okay? And in some cases, you will see this on a lab report as being COP, colloid osmotic pressure. saying that, okay, this protein is wrong, out of balance, blah, whatever the case might be, and it's affecting the flow of the blood. They can actually be able to look and see the actual proteins in the blood, like those fibrinogens, the globulins, and so forth. When I say we've come a long way, we have come a long way in the study of blood. It is totally amazing to me. Now, real quick before you go on break, actually, will y'all work with me? Let's lecture till 10:30, take our break, come back into a lab. Okay, because I'd like to get through this right here. All right, because I mentioned that our red blood cell, the red blood cell is not at maturity going to have the cell components, the cell organelles. When we talk about our production of blood, it is continually replaced. On a typical day, an adult, look at this, 400 billion platelets. I don't know about y'all, but I like to have that in dollars. Okay? Same thing for 200 billion red blood cells. I'll take any of these. All right? 10 billion white blood cells in a day. See? The production of the blood and these formed elements, which are my platelets, my red blood cells, my white blood cells. The production of it is called hemopoiesis. Anytime you hear the term heme, think about the blood, okay? Because there's a reason for that. Hemoglobin, all right, it's really cool. We have in our body hemopoietic tissue. Tissue that will give rise, or tissue that helps blood production. Goes all the way back to sperm meeting egg, fertilization occurring, one cell becoming two, two becoming four, layers getting formed, and we get the yolk sac. Think about a chicken egg. Same concept. Yolk sac. It gives rise to little blood islands. They produce some very primitive stem cells. They begin to migrate to tissues that are going to form the bone marrow in that embryo. They're going to go to the liver, the spleen, the thymus, and then as the embryo is forming until time of birth, these areas, the bone marrow, the liver, the spleen, and the thymus, help with blood production. After birth, it's only the bone marrow. The rest play a huge role in the blood. Trust me on that, okay? Now, once baby is born, baby comes to us, teeny tiny, unless, have y'all seen that lady that gave birth to like the 14 or 15 pound baby?
Oh, wow.
Oh, man.
She should have had a C-section.
I can't remember if it was natural or C-section, but anyway. Anyway, okay, so, itty bitty baby gets here, all right? Itty bitty baby, a whole lot of it is cartilage and so forth. And it